Now we'll see some more examples using partial fraction decomposition in order to evaluate integrals. So to start, consider the integral of 6 over x squared minus 1. So here, again, I want to recognize that I could factor the denominator. So I'm first going to observe that this is equivalent to having in the denominator x plus 1 times x minus 1. Once I've done that, then I know that I can try to use partial fraction decomposition. And if you recall from our previous example, what I want to do is take that integrand and set it equal to a over one of the factors plus b over the other factor. And we want to try to find the value of those constants. The next step was to multiply both sides by the common denominator, leaving us with, in this case, 6 times x minus 1 plus 6 equals a times x minus 1 plus b times x plus 1. So notice, unlike our previous example, the left-hand side is constant. It doesn't depend on our value of x. So when I go through the process of plugging in particular values of x, in this instance first, I will plug in x equals minus 1. The left-hand side just stays 6. But plugging in minus 1, I get a times minus 2. And of course, I get b times 0. So from this, I'm going to see that a must equal minus 3. Likewise, I plug in the root plus 1. Has no effect on the left-hand side. I take a times 0, and I'm left with b times positive 2. So b is equal to positive 3. So what that means is the integral 6 over x squared minus 1 is now equal to 3 times the integral of 1 over x minus 1 minus 3 times the integral of 1 over x plus 1. I can write this now as 3 natural log x minus 1 minus 3 natural log absolute value of x plus 1 plus c. Again, this is a suitable way to write our answer. I alluded to this before, but I can simplify the log expressions, and in fact, the textbook typically does. So I'll point out that you could observe, first of all, that you could bring in those 3 multipliers to write this as the log of cubes. And then the other thing we could do is recognize that we have the difference of 2 logs, and we could write this as a single log expression if we took this into a quotient here. So this is another correct way we could write this answer. So the next thing I want to address, because we'll see that a lot of these examples are very similar if I just go through several different factoring situations. So to address some of the things that could be slightly different, one thing that will make it harder is something like the following. So a lot to write here. I have the integral of 2x cubed minus 11x squared minus 2x plus 2, all divided by 2x squared plus x minus 1. So something I've neglected to say up until this point is that when we're using partial fraction decomposition in the way that we did in the last 2 examples, we really need it to be the case that if you look at the degree of the numerator, it is less than the degree of the denominator. And that's true of what we've seen so far. As soon as you get an example in which the degree of the numerator is greater than or equal to that of the denominator, we have to actually do something first to rewrite this before we can use partial fraction decomposition. So I'll point that out. When the degree of the numerator is greater than or equal to the degree of the denominator, what we have to do first is use long division to rewrite that integrand. So it very well might have been a long time since you've done long division in a context like this. So let's recap that. So I want to take 2x squared plus x minus 1 and I want to divide that into 2x cubed minus 11x squared minus 2x plus 2. So in order to do this, I start by taking this denominator and thinking, what would I have to multiply it so that its first term matched this 2x cubed? We'd have to multiply by x. So I put x up there, and then I actually do multiply that. X times the denominator would give me 2x cubed plus x squared minus x. So we want to take this and subtract it from the numerator. The cubic terms will cancel. We'll be left with negative 12x squared. And then we have minus 2x plus x. So we're going to now get minus 1x and then plus 2. Now I want to look at this and think, what do I have to multiply our expression by here so that the first terms would match? And notice that I can do that with a minus 6. Oops. So negative 6 times the denominator would give me minus 12x squared minus 6x plus 6. Again, I subtract that from what's above. The squared terms now cancel out. I have a negative x minus a negative or plus 6x, so positive 5x. And I have 2 minus 6, so we get negative 4. As soon as I get to a point where what's left here has a degree smaller than the original denominator, then I can stop with long division. So we're at that point now. This has degree 1, the denominator has degree 2. So what this means is that the integrand that we started with, which is this, we performed long division to be able to rewrite that integrand, and then consequently I'm going to rewrite the integral. So we're saying that that expression is going to be equivalent to the x minus 6 plus the remainder, which was 5x minus 4, over the original denominator. So what's happened here is this first integral, we can find that right away. The antiderivative here, I get x squared over 2 minus 6x plus a constant, but I'm going to have to just introduce 1 at some point. This one, we can use partial fraction decomposition. So let's do that now, and then we can put it all together to finish this off. So now I have 5x minus 4, which you can start to scroll up, and the denominator will factor into 2x minus 1 times x plus 1 now I can scroll up. So we want to write that as a over one factor plus b over the other. Again, I multiply both sides by the common denominator, and this gives us 5x minus 4 equals a times x plus 1 plus b times 2x minus 1. We plug in our root values of x, one of it which is 1/2. So here, the left-hand side does depend on x. So 5 times 1/2 minus 8 over 2 would give me negative 3/2 on the left-hand side. The b value will be multiplied by 0, but I have here a times 1/2 plus 1, or 3/2. So this gives me a equals minus 1. The other root we can plug in here is negative 1. And when we do that, we get minus 5 minus 4, so negative 9 equals a times 0, and b times negative 3. So b is then equal to negative 9 over negative 3, or positive 3. So putting all of this together, I'm going to go back to what we started with. So we have the original integral which had a lot of pieces. We then used long division, and we broke it up into 2 pieces. And we've already, remember, gotten this one term here. This was the x squared over 2 minus 6x, plus an integral that we now have used partial fraction decomposition on. And so we've broken that up into the minus 1. So pull that minus out. 1 over 2x minus 1, plus 3, the integral of 1 over x plus 1. So the last step here is I want to actually evaluate these integrals, and then we'll be done. So we get x squared over 2 minus 6x, carrying that through. This one is going to give me 3 ln x plus 1, and I have this constant. And I want to point out here that we have to be a little careful. So turns out we will get this. But a common mistake is to leave it like this. But one thing that's significant here that we haven't had in these examples is there's a coefficient on x that's 2. So if you check the derivative of log of 2x minus 1, you would get 1 over 2x minus 1. But the chain rule would also mean that you have to bring out a times 2. So this is not the correct antiderivative. One way to solve this is think that in order to make sure I don't have a multiplier of 2 when I differentiate, we can satisfy that by putting in the reciprocal of that constant. So that will always work. I still have a linear factor. Again, if that's unclear, you could go through the motions of actually letting u equal 2x minus 1. And that 1/2 would come in from your du equals 2 dx. So this is important. I'm putting it in red just because that's something that I commonly see left off. But importantly, we are done with this example. And finally, I want to just do one final example here about what else could be different from what we've seen above. And we're still with the constraints of having linear non-repeating factors. But we could still solve something like the following. 1 plus x squared over x plus 3 times x plus 5 times x plus 7. Now, I still have non-repeating linear factors, but the examples we've seen so far have 2 such factors, and here we have 3. So what I want to kind of demonstrate in this example is that as long as they are linear and you have no repeats, you could have as many factors as you want, and that's going to dictate how many constants we have to solve for. The other thing that is significant after our last example is the degree of the numerator is smaller than that of the denominator, so we do not need to start with long division. So here I take my factored expression, which this one is already factored for us, and my goal is to be able to express it now as a over one of those factors plus b over another of those factors, and then I have to bring in a c to account for all 3. So we're solving for 3 separate pieces here. Again, multiply everything by the common denominator, leaving us with 1 plus x squared over here. And notice that when I multiply the first term here by this common denominator, the x plus 3's will cancel, but it's going to leave me with 2 factors up top. And that's going to happen with all of these. The one that's in the denominator will cancel, but the other 2 factors will stay. So again, this looks messy, but our same strategy is going to work out nicely. There are now 3 roots to the original denominator. One of those is minus 3, one is minus 5, and one is minus 7. So notice that I can once again plug those in. On the left-hand side, 1 plus minus 3 squared is going to give me 10. And what's significant about this is both b and c are multiplied by x plus 3. So when you plug in x equals minus 3, that's going to wipe out both of those terms. So it really allows me to focus on just the unknown a. Plugging in minus 3, we have a times 2 times 4. So with that, I'm going to have 8a equals 10, or a equals 5/4. If I plug in -5, that's going to wipe out A and C. So we're going to get 1 plus 25, or 26, equals B times -2 times +2. So B would be -26 over 4, or -13 over 2. And then finally, we can plug in -7. That's going to wipe out both A and B. We're going to get 1 plus 49, or 50, equals C times -4 times -2. C then is going to be positive 50 over 8, or positive 25 over 4. So now what we're able to do is rewrite this so that our original integral is equal to the integral of these three pieces that we've introduced. So we have 5/4, the integral of 1 over x plus 3, minus 13/2, the integral of 1 over x plus 5, plus 25/4, the integral of 1 over x plus 7. On each of those, notice that the coefficient of x is 1, so I don't have to worry about bringing out 1 over the coefficient like I did in the last example. So this simply leaves me with 5/4 natural log absolute value of x plus 3 minus 13/2 natural log absolute value of x plus 5 plus 25/4 natural log of absolute value of x plus 7 plus an arbitrary constant. And again, this is a perfectly suitable way to write it. Alternatively, we could go through and combine those log expressions like we looked at in the first example in this video. So that wraps up a look at our 3 integration techniques. So the practice here is going to be really important in order to start to get the intuition, first of all, about how to select the right U. How do I choose U and DV and so on? But also, the other thing that is going to make this difficult is how do I decide which of my integration techniques to use? So we've kind of split these up into videos. Discussion will be really useful for giving you that practice of having an integral and now trying to decide, how am I going to solve this? Is there more than one way? If so, is one way more efficient? So the more practice you get, the more intuitive that's going to become.